Okay, you're hearing clearly online? If it sounds a little muffled, you'll let me know, right? Jaya, hearing okay? Cameron? You're hearing okay. So if it sounds a little muffled, let me know, right? All right. So we're moving on to some other thermal quantities, right? So far, we looked at kinetic theory of gases, and we looked at how pressure, volume, and temperature are related. So we're going to change this now. I can't use the simulation, right? They give me some trouble, right? I'll just do it back on the board like long time. Right? I'll send you a link for the simulation so you can see how it's working, right? So our next heading is thermal quantities, specific heat capacity. Yeah. Specific heat capacity, really easy. Specific heat capacity. Really easy. Probably the easiest thing ever. Really easy. Specific heat capacity. I usually say no. Oh, they have this already, right? Yeah, master right. Specific. Finish. All right. So let's take a look at this new thing called, right? Let's look at this new quantity called specific heat capacity. Right? I just waiting on those to come back next. Right? So draw this quick, and I want to give you a small explanation, right? On what is specific heat capacity. Right? You'll see that writing online there. Nice. Right. No, you're not seeing the writing, Jose? No. Watch it. The simulation not working, right? So we can leave the group. Yeah, you can leave it. It's blurry. Oh, it's blurry. How much else blurry is that? And I'll fix it. Yeah, everything I can flow is my Wi-Fi. So, well, I start my Wi-Fi. Yeah, the Wi-Fi bad. The Wi-Fi here a little bad. All right, I'm going to write a little bit larger. Right? I'm going to write a little bit larger, right? Hold on, I'm going to see how it's looking on YouTube. It's clear now. Yeah, the Wi-Fi is kind of bad. Grace, you got to log in, huh? Right, you got to log in again because the simulation is not working. The Wi-Fi working too bad today. Hold on, let me just check out how it's looking on YouTube. All right, still too far behind on YouTube. I'll come back and check this now. All right, so I'll go back and draw a little bit bigger, right? The heading is still specific heat capacity. Let's go a little bit bigger. Right, so you join a block. Inside the block, I have the word here mass. You're seeing that? And then I join a little arrow here to represent I'm going to heat this mass. Y'all see these words here? Yeah? Okay, good. Right. If it's real blurry, let me know, right? I'll just keep writing kind of large. So I'll just use this area here and just keep writing large. Right. What is specific heat capacity? Watch here, right? What is specific heat capacity? Exactly what the word says, right? The word is basically saying that it's saying the capacity of heat that our object can take, right? So when they use the word specific, here's what they really mean. They want to know the amount of heat that a specific mass can take before there's a temperature change. All right. So let's see, let's stick a little thermometer in here. Right, and we have an initial temperature. Let's say theta 1, theta I, that is your initial temperature. Right. Here's what specifically capacity is. It's the amount of heat required to change the temperature of a particular mass. Okay with that? That's how simple it is. Some materials need more heat for a specific mass to change temperature, right? While some need less. So this quantity called specific heat capacity, and the symbol is lowercase c, right? Lowercase c, which is specific heat capacity, is the amount of heat energy, right, required to change the temperature. That symbol is changing temperature of a particular mass, right? So C is what we call specific heat capacity. M, that is your mass. And delta theta, that is your temperature change. Right? That's the temperature change. And last thing, E is the heat or the energy. Right? Sometimes you'll use heat, sometimes you'll use thermal energy. So a very small, a very simple explanation of what is specific capacity is the amount of heat energy required to change the temperature of a specific mass. That's okay? And this is a little formula showing the relationship. Specific capacity is the energy required to change temperature of a particular mass. So we need to learn this relationship here. All right, copy it down. How do you write in looking there? All it's still blurry. Logging set. My log out. And while logging, right, copy it down. Copy it down, we're gonna apply it. Better, okay. Yeah, just the Wi-Fi. I just want to see how it looks. Right. While you're writing, we need some SI units, right? SI unit per mass is what? Kilograms. We could also use grams, but let's just use kilograms for this example. What's the SI unit for temperature? Kelvin. What's the SI unit for heat energy? Joule. Right. Do me a favor now. What's the SI unit for this? Think about it first. What do you think is the SI unit for specific heat capacity? Think about it first, huh? Let me put it right there. What do you think is the SI unit for specific heat capacity? Why you enjoy the look now? Somebody looking at? Sorry? Joules per Kelvin per kilogram. Yeah. That could work, right? Energy is in joules. Energy is in joules. Mass is in kilograms. Temperature is in Kelvin. So you can write it like this. Joules per kilogram per Kelvin. right? Joules per kilogram per Kelvin. All right, so that gives us an idea of what is specific heat capacity. All right. Before we transform, actually, let's do it one time. Can you make E the subject of the formula? Can you make E the subject of the formula? Yeah, big one. E is, can I just pass one line there? But yeah. What it says? Somebody can make E the subject of the formula there? Where we at? E is equal to by, yeah. So the formula is MC delta theta, right? You're seeing that? Cross multiply, right? It's like two fractions equal sign cross multiply, right? So again, E is equal to MC delta theta. Are you okay online there? Right? And this energy is basically the energy needed for a temperature change. Energy needed for a temperature change. Right? Okay with that? Right, so let's make another that little formula there. We'll be using it a lot in a little while. Okay with that? Right. Before we start doing any little examples on this, right? This formula this quantity is called specific heat capacity, right? I would like to create, I would like you to help me create a definition for something called heat capacity. So I don't want it, I want to exclude this. What will change? Huh? What do you think will change? Anybody can answer online? Anybody here? I would like a definition now for heat capacity. Heat capacity is no longer common C, it is capital C, right? Uppercase C. The capacity of heat, the amount, right? Mass, but I the exact thing. Something has to change, right? What? Specific heat capacity was the energy required to change temperature of a specific mass, right? That was small c. Now I take off the word specific, and I would like the definition for heat capacity. I'm gonna see online. Somebody sent something online here. Oh wait, no. What will change? Like, what will be that definition for heat capacity? If you had a guess, Ricardo, my name. Huh? Heat required to change temperature. Good job, Katrina. So what you say? What will change? Heat energy required to change temperature, but the mass doesn't matter. They're not interested in mass. So heat capacity is taking off the mass. And you will say that heat capacity is energy required to change temperature. That's it. Right? And the SI unit is joules per Kelvin. All right. So write this down. Heat capacity. Heat capacity is the temperature. Sorry, is the heat energy required. Heat capacity. Heat capacity is the heat energy required to change the temperature of a substance. To change the temperature of a substance. While specific heat capacity, you have to write the whole word, right? While specific heat capacity, or repeat the first part, heat capacity is the heat energy required to change the temperature of a substance, while specific heat capacity is the heat energy required to change the temperature, while specific heat capacity is the heat energy required to change the temperature of a specific mass of the specific mass of a substance. To change the specific mass of a substance. To change the temperature of a specific mass of a substance. I'm going to call it over here again. You make a mistake there. The heat energy required to change the temperature of a specific mass. Change the temperature. To change the temperature of a specific mass of the substance. Right? So write this for heat capacity. Write this for heat capacity. And we already have this for specific heat capacity, right? All okay with us? Right. All okay with us? Yeah, right. Now I need more maths than physics. I want a relationship between big C and small c. I want a formula that relating big C and small c. Look at this, right? This is what you're working with, right? You're working with C is equal to E over delta theta. And you're working with small c is equal to big E over M delta theta. But here's what I want. I want a relationship between two of them. I want them together. I want two of them together. It's more maths than physics, right? Let me see what you will do. If you get message online. All right, well, Cameron have it already. Malini, you got you?
The big C is heat capacity.
Huh?
Big C is heat capacity.
Big C is heat capacity, small c is specific heat capacity. Look at what you're working with. I want you to come with a relationship and show me your steps. I know some of them know the formula. I want you to show me your steps. To show you that. Huh? All right, let's check out online if anybody, nothing online, channel, nothing. All right, here, watch. I'm gonna give you a little help, right? So small c, what? Small c is equal to E over this, right? Which is the same, I'm going to write this a different way. E delta theta by 1 over m, correct? Is this the same as this? Yeah?
Yeah.
E by 1 is this by this is this. Nice. What this is here? What this is? And I big C. So small c is equal to big C multiplied by 1 over m. Correct? Can I bring 1 over bring m here? So you will get MC is equal to big C. Or more formally, big C is equal to m by c. Right? So that's a relationship between heat capacity and specific capacity. Yeah, let's show you how it looks more formally, right? Look like that. That's okay. So you kind of had it there, you know, Malachi. Kind of had it. Kind of had it there. Everybody okay with that? All right. Let's do some small calculations and then what? I can't do the simulation today, but I can still show you how to do some calculations, right? Everybody okay with the concept of these two quantities? We have one more quantity to look at, but not today. But that quantity doesn't cause a temperature change. It causes a phase change, right? And somebody was talking about this earlier. It's called latent heat. All right. So when I apply heat in our examples for today, it will cause temperature change. All right. So head up and listen to some example. Example one. Example one. Yeah. Why not? Yeah. Right. Right. Example number one. A block of mass 5 kilograms a block of mass 5 kilograms is heated. A block of mass 5 kilograms is heated so that it undergoes so that it undergoes a temperature change of 10 Kelvin. So that it undergoes a temperature change of 10 Kelvin. Right? Full stop. If 10 joules of heat was applied, if 10 joules of heat was applied, what is its specific heat capacity and its heat capacity? So I want to find small c and I want to find the big C. Right, read it again. Read it again. Right, I draw a little diagram here and I'll show you all the quantities. Remember, any question you have, try to write out all the quantities. Read it again. Write all the quantities they give you. They give you mass, they give you temperature change, they give you energy. And they want you to find small c. So what formula is that? E over m delta theta, right? Right? So the energy is 10, the mass is 5, temperature change is 10. When you work this out, they'll cancel, you'll get 1/5 or 0.2. Write the correct SI unit, joules per kilogram per Kelvin. But okay with that? Right? How we would find heat capacity now? What would that be? Right? Energy over temperature change. Right? Energy over temperature change. So that's 10 over 10. That's 1 joule per Kelvin. So it takes 1 joule to change to 1 Kelvin. Here it takes 0.2 joules for every kilogram to change to 1 Kelvin. Copy down? Any questions online? Yeah. Cool. We like on or it works. You come in front. Well, stay there until cool. Jack it up. Right here, nice and warm. Actually, look, in here warm. Yeah, here warm. I feel real hot. Right, but you okay online? Any questions online? Barrage, any question? Shannon, look, everything right here, Shannon. Right? Everything right here. Okay, let's go again. Let's go again. I changed the question around, right? Find the energy required. Yeah, let's think a little bit for this one. Number 2, find the energy required. Number 2, Right? Find the energy required. Find the energy required to change the temperature of to change the temperature of 0.5 kilograms of water from 35 degrees Celsius to 50 degrees Celsius. Right? Find the amount of energy required to heat energy required to change the temperature of 0.5 kilograms of water from 35 degrees Celsius to 50 degrees Celsius. Note that the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Oh, sorry, 200. Go ahead. Think about it. Let's see how we do it now.
I wasn't so you
I could try. I want to come up. They'll come this year. Almost come last year, you know. No, almost came to the marathon actually. Yo, watch you kind of when it prepares on come on. But you all start and finish anymore. But you all start and finish anymore. Like start by the school. Hmm? All right. Try this. All right, so let's show you come up with now.
I don't know.
Yeah, okay, all right. I'll give you a minute, I like when you're trying. So see if we can find that energy there from online. So we can find the energy. So use the energy formula. Oh yeah, try that there. We got some more. All right, so let's check out number 2. Any answers online here? No answers online? Nothing? All right, so let's see. So, of course, we have to find energy, right? And I told you the formula already. E is equal to mc delta theta, right? We know the mass, right?
Yes, sir.
The mass is
2.5.
0.5. We know C is 4200. And the temperature changes how much? So the temperature changes from 50 to what? 35 to 50, right? So the temperature changes. Watch, I want to show you something here. Right? If you look here, temperature must be in Kelvin. Are you okay with that? This temperature, but let me show you. It will still work out, right? This temperature is in degrees Celsius. So how do we get a temperature change in Kelvin? Watch this here. If you have 50 degrees to 35 degrees Celsius, we get in 15 degrees Celsius as temperature change, right? If I were to convert this to Kelvin, how much I'll get? Add this to 273. How much you get? 323, right? And here, if you add this to 273, 348. Sorry, that's Kelvin, right? If you subtract this, how much you'll get? Same thing. Check it and see, you'll get the same thing. Right? So here what this is saying, right? Here what it's saying, I'll write this down. A temperature change in degrees Celsius. A temperature change in degrees Celsius is the same as a temperature change in Kelvin. A temperature change in degrees Celsius is the same as a temperature change in Kelvin. Yeah? No, so that's what's saying here, right? If you find the temperature change in degrees Celsius, you would have gotten the same answer if you had changed the Kelvin and worked it out. So it don't matter, right? It don't matter. But I don't want you to watch this all here. I don't want you all to subtract here and then convert to Kelvin. That is wrong, right? You have to convert to Kelvin before and then subtract, or just leave it because you're getting the same numerical answer. Are you okay with that? So a temperature change in Kelvin is the same temperature change in degrees Celsius. Jaden, you understand that? Everybody okay with that online? Ishana? Right, so it doesn't matter what you do for your temperature change, right? What unit it's in? It's the same temperature change. So make a note of that, please. And then help me out here, please. How much is it? 0.5 by 4200 by 15.
About 31,000.
Huh? 31,000.
Say right, Justin.
Yeah. My head already. All right, nice. Okay, so that's the amount of energy required to change the temperature of what, yeah?
So you take a bit, 1.5,
Kilojoules?
10 to the power.
Yeah. It's 31.5 by 10 to the 3. I'll even take 31.5 kilojoules. There you go again. What you want to do with it? You gotta take it off. Take it off. I thought you're feeling good. You feeling good? Well, it's just too. I tell you, come and sit down here. Come and sit down here. Come and sit down here. Who's that? What is Come and sit down here so I don't feel warm now, boy. All right. I'd rather say that. I ain't studying here again. Number 3 now. Let's go again. Number 3. Number 3. Let's go again. Right, I'm giving you water again, right? Water is a simple value to use, right? Number 3. Find the amount of heat energy required. Find the amount of heat energy required. Heat energy required to change the temperature of water. To change the temperature of, to change the temperature of 10 grams of water. To change the temperature of 10 grams of water. 10 grams. From 50 degrees to 70 degrees. From 50 degrees to 70 degrees. Grams a kilogram is divide. Same for 200. Same SI unit. Same SI unit. Joules per kilogram per Kelvin. There's a standard value here. There's a standard value for water. Water is always 0.200. But I will show you what I'm going to change in a little while. Try that. Find the energy required to change that temperature. Those who are online, work it out, message your answers.
Yes, I am.
Hurry up. Same value.
Okay.
Right, same values. Right, those who online message your answers, try and send the unit, right? Jaya sent hers. Looking correctish. Right, any more answers online? Only I only have one answer. I have two. Maria is correct. Jaya is correct. I don't have anything from Shannon, from Ishana, from Cameron, Jose. Yeah, it's 10 grams of water, Katrina. Send some answers, please. The easy one here. Samir answers. Sahara answers, please. Keelan, are you there? Keelan, you there? Jose, check back, right? Correct, Viraj. Send the SI unit as well, right? Can the habit of putting in the SIU unit as well. Come, Keelan, send an answer now. How much you get? How much you get, Mr. Keelan? Shannon, you forget to convert the grams to kilograms. Hmm? All right, number 3, the mass is what again? 10 grams, right? So you have to divide by 1,000 to convert to kilograms, right? So it's 0.010. They gave us the same value. And the temperature, oh, watch this here. See this value here, really important. Huh? See if this is in kilograms, right? Then this must be in kilograms. If this is in grams, this will be in grams, right? So you have to look at this. I'm going to change it for you just now, right? And the temperature change is what? 70 to 50, 50 to 70. That's 20. So the energy, and look at the way I watch Malachi. Watch the way I write in a solution. I write all the quantities, and I'm going to write the formula. And I'm going to make a substitution. Then I'm going to write the answer.
That kilogram, the 0.01.
0.01, yeah.
Or the 0.
Yeah, I just put it 0.
So
Right.
I would say,
Yes, sir. The way marks are allocated is like this. How much you got here? 840, right? Here's how marks are awarded. Formula, substitution, answer. So it's to say submit in your brain as well. All right.
my apologies.
Yeah. So it's 840. Are you okay with that? Let's go again. Ready? Yeah. Given that a liquid has a specific heat capacity, given that a liquid has a specific heat capacity of 9.2 joules per gram per Kelvin, given that a liquid has a specific heat capacity of 9.2 joules per gram per Kelvin, Full stop. Determine the temperature change that is possible. Determine the temperature change that is possible. Determine the temperature change that is possible when 250 joules of energy, when 250 joules of energy is applied to 1.5 kilograms of the liquid. 250 joules of energy is applied to 1 kilogram. Yeah. Is applied to 1.5 kilograms of the liquid. 1.5. Try that. Do this again. Look how I answer the question. I write down all the quantities given, right? C, D is how much again? 250. 250. Any answers online? Let me see. I've seen some answers here already. Right, so you have to be able to make the subject of the formula, right? So if I make theta the subject, temperature change the subject here, I'll get temperature change is equal to energy over MC. That's okay? You have to learn to make the subject of the formula correctly, right? So I just carry across the MC and it becomes E divided by MC. All right, and how do we work out that now? Let's see. E is equal to 250. M has to be in what? M has to be in gram because it have grams here, right? So M has to be in grams. So that'll be what? 1500 grams. And C is what? C is your 9.2. How much is that? 250 over 1500 divided by 9.2 is how much? 18.1. Check it out. What's the answer? 0 point. What's the answer there, Olia? How much is that? How much? You divide this again, 55.2. It's almost 10. This should be way smaller than that. Yeah, 0 point. Katrina got 0.018. Yeah. Check it back in the calculator. I just check it back in my head and know it's something. It had to be something small. Look at it. Look at the numerator. Look at the numerator. Right? Okay. There is nothing. Oh, remember I gave you this mass. I gave you this mass here, right? I gave you the mass in kilograms, right? But the unit here is joules per gram. Huh? So you have to look at this. The energy has to be in joules, the mass has to be in grams, and the temperature has to be in Kelvin. So this gives you an idea of what to work in. Okay, so I converted this here to grams here and I work it out. Okay, so it's very important that you look at the unit, right? Good job, Amalini. So Samir, follow this. Samir and Keelan, I find you all not sending many answers, eh? Samir and Keelan, send answers to me, please. So at least know what you did, right? So here in this question, the lesson I want you to learn, Ricardo, right? I want you to learn to pay attention to the units here. Right, Ricardo? Pay attention to the units here, right? All right. Next. Fraction. Right? 250. All right. Good. What time it is? Oh gosh. Anyway, I don't know. Now we still have enough time. So what was the answer? What was the answer? The camera icon blocking. Oh, that camera thing blocking. I wonder how to move that way. The answer is 0.018. 0.018 K. Oh, okay. I didn't know that was, I thought that was only show up on my computer. Okay, all right. Right. One last thing. Next day we'll continue from right here, but one last thing. Right, so I need some help, right? I need some help here. I want to determine how to determine the specific heat capacity of water. Right? So here's the problem. Watching. I have a container and I have water in it. And I would like to find C. Right? I want to find C. I don't know what is C for water. Right? What to do? How do I find C? So C is equal to energy over M temperature change. Right? So I need some ideas. How do I find E? How do I find M? How do I find temperature change?
Well, we have to get we have to weigh.
Right? Right? Weigh the water in the container by itself. Right? What do we do after that? Right? So I'm finding the mass of the water and container. Then I'm minusing the mass of the container, right?
Yeah.
Right? Yeah.
Very good.
How again the temperature change now? Use a thermometer, very good. Find the final temperature minus the initial temperature. Very good. One last thing and we're done. How we gain energy? How we gain the energy? We can't just turn on the Bunsen burner or turn it on. Or turn on the heater. It's usually how you get value. Any ideas online? How we can get the energy delivered? Anybody online? Yeah. Six. Hey, when you messaging me? Any ideas online? How do we find that energy? Adele, any ideas? How to get and think of any formula you know to, yeah? Yeah. Shh. Huh? Well, we do have C as well, so you can use that. Force times distance. You get in there, but we do have force and we do have distance. That'll be kind of hard. Anything else with power? Anything else with energy? Very good, Ishana. Ishana said to use the power multiplied by time. But care what you do, right? Right? How we get power? How we get power? Right? Now something simple. When you use something called an immersion heater, right? When you place the immersion heater in there, the immersion heater has a power rating. So it has a value, right? And then you could use a stopwatch to get the time. Right? So you could use This is the lab that you will do.
What?
So you will use a power rate, you will use a immersion heater,
So I don't know.
place in water, and then use the power rated. Next week, we're doing this lab here. It's right here.
So bring one up.
No, we're doing the lab, okay, we're in the notebook. Right? Next week, we're gonna do the same lab here. All right, so let's make a note of this. We are going to find the specific capacity of water. All right? Well, yeah, if all want to come face to face and do it here, but those who online, I will
To force them to come.
stream it, yeah. No, if they could come, let them.
Force them.
Right, so next week I'm gonna do a small. I'll do a lab, right? It won't take long. All right, so that's it. You all can log out. Those who hear face to face, I'm gonna have to just take this question here next day before you enter the lab. Yeah, to make sure you know what you're doing.
I can just keep it on for.
All right, so nice. That is it online. You all can log out next.